My project focuses on the study of modern brachiopod shells coming from different geographic settings and different water depths. Brachiopods are sessile benthic marine invertebrates with a bivalve shell and a lophophore feeding structure. They actually form an ancient lineage that has inhabited seas and oceans environments since the early Paleozoic. The aim of my study is to increase the knowledge on brachiopod microstructure to test their fidelities as archives of paleoclimatic and paleoenvironmental proxies. It aims at answering a main question which remains still unresolved, which is if microstructural patterns are controlled at the interspecific, intraspecific, or ontogenetic level. Brachiopod shells are considered one of the most reliable high-resolution archives of climate and environmental change, as they precipitate a low magnesium calcite shell, which makes them resistant to diagenetic alteration. They are abundant and widespread in the fossil record, and they precipitate their shell close to isotopic equilibrium with the ambient seawater, with limited vital effects. They grow their shell by marginal accretion, producing sequential growth increments, which can archive geochemical variation, which can then be exploited to make climatic and environmental inferences. However, to do so, it is needed a solid understanding of biomineralization processes and how the shell is built and how geochemical signals are incorporating in the different microstructures. And that's why I'm addressing this in this study by studying modern brachiopod shell microstructure. The previous research has focused extensively on the micro and nanostructure, whereas what remains poorly constrained is the shell architecture at the mesoscale. This means the spatial organization, arrangement, and thickness of the different shell fabrics at the scale of hundreds of micrometers to few millimeters. In addition, most geochemical analyses in literature are based on bulk measurements, which means that they combine the different microstructure within the shell. So even if it has been seen an intra-shell ontogenetic geochemical trend, the relationship between microstructure and geochemistry still needs further exploration by high-resolution in situ geochemical analysis. I studied 8 species of modern brachiopods belonging to the orders Terebratulida and Rinconellida. I performed a microstructural analysis using a scanning electron microscope to assess the organization, arrangement, and thickness of the different shell layers. These are an outer primary dendritic layer and an innermost secondary fibrous layer. This is the typical shell sequence for all the brachiopods. For the 2-layer shells, which are here in brown, they develop just the primary and the secondary layer. But there are some species here in bright blue which also develop a tertiary columnar layer. I merged all the SEM images to reconstruct the entire shell cross-sections. And here are the results for the 2-layer species. They display the typical shell architecture with an outer primary layer and an innermost fibrous secondary layer. And in the SEM image, we can appreciate the species Notosaria nigricans from New Zealand. And this is quite interesting as the primary layer thickness is between 50 to 70 microns, whereas it has been reported in literature that the primary layer thickness ranges between 20 to 40 microns. Another interesting species is Liotirella uva, which is an Antarctic species widely studied for its microstructure and its geochemistry. It has always been considered a two-layer species. However, as we can see from this SEM image, there is this layer with prism-like elements which are resembling the columns of the tertiary layer, and this may suggest that this species is also developing a tertiary layer, and so could be possible that it might be considered a three-layer species. Another interesting feature is that we have this region in orange in the inner part of the shell section, with irregular and angular fiber morphologies. This is related to muscle attachment sites, and it is particularly important to have found this feature in modern brachiopods, since when we are dealing with fossils and doing diagenetic screening, what we normally, if we normally see something really altered as this microstructure, we end up thinking that some diagenetic processes were acting, whereas if we can locate this region is in the innermost part of the shell, we might also end up considering that that might be related to muscle attachment sites. And finally, at the anterior margin, we have these calcite pads, which are related to a temporary interruption of the biomineralization due to the retraction of the mantle. Now we see the results for the three-layer species. So in addition to the first two layers, they also biomineralize a columnar tertiary layer. And we have two three-layer species, Gryphus vitreus from the Mediterranean Sea and Liotirella neozelanica from New Zealand. They are quite comparable in their central region and anterior region. In the central region, we have, for both of the species, a huge block of columns, whereas in the anterior region, the tertiary layer is decreasing until disappearing, and we have the secondary layer dominating over the tertiary. The two species actually differ in their posterior region, since in Gryphus, it is quite comparable to the central region. And so we have still this huge block of tertiary columnar layer, whereas in Liotirella neozelanica, the secondary layer is still dominating over the tertiary, and this microstructure is more complex, and the columns are intercalated between the stacks of fibers. So we have seen that the two species differ in the posterior region for their microstructure. However, it has been reported in literature that there are comparable geochemical patterns between the two species, in particularly a U-shaped trend for trace elements and a reversed U-shaped trend for carbon isotopes. But having said that, the microstructure is different in the posterior region, for my consideration for now is that microstructure does not exert a primary control on geochemistry. However, I will further explore this relationship by doing high resolution geochemical analysis using a laser ablation system in order to target the different microstructures of the shell. Concluding, we have seen the main differences between the two-layered and the three-layer species for modern brachiopods. And as we said, to understand the influence of microstructure, but also of vital kinetics and even environmental effects on shell geochemistry, we must perform some high-resolution geochemical analysis, which I'm currently doing for my PhD, in order to test the fidelity of brachiopods as archives for proxy-based reconstructions. And thank you for the attention.